So we're going to go over these basics of topic 9. You're going to follow along in your notes with your reference tables and also with this note sheet. We have a chart here about everything you would want to memorize about oxidation reduction, and on the back, everything you would want to memorize about the differences between voltaic and electrolytic cells. If you really do memorize these two charts and how they are put together, you'll be in a very good position to answer any Regents question about oxidation reduction. But instead of starting with these charts, I'm going to show you how I would reconstruct them from memory. First, though, we need to look at oxidation numbers. Once we're done with this video, you should start on your topic 9 questions out of your various packets. So these questions out of these 3 packets. Okay, oxidation numbers. Basically, why do we have these numbers? What do we do to keep track of them? Okay, the numbers are really just a fancy word for charge. And there's a couple rules. The first rule, the simplest rule, is the most important, which is elements that are alone, pure elemental, have 0 charge. Their oxidation number is 0. So as an example, I'm going to show you a reaction that is a redox reaction. You're going to recognize it as a single replacement reaction, I hope. And the first thing you'd want to notice is the aluminum by itself has 0 charge, an oxidation number of 0. The iron by itself, the sad-lonely single guy, has an oxidation number of 0. Find those guys first, and you'll be in a good place to figure out what's going on with oxidation reduction. Then, in the compound here, there are positive and negative charges hiding behind here, right? And there are positive and negative charges hiding in here. So, how to do an oxidation number in a compound. In a compound, the total charge adds up to 0. There's a lot of specific rules, but instead of memorizing a lot of rules, I just want you to use the possible oxidation states off your periodic table and make sure it adds up to 0 and make it make sense. So, let's do the iron bromide here. FeBr2. All the charges have to add up to 0 because it's a neutral compound. Okay. Whatever the oxidation number on the iron is, if I add it to the oxidation numbers of 2 bromines, it would add up to 0. Now I'm going to do it this way, 2, and I'll put the oxidation number of each bromine in parentheses there. I don't want you to think that the 2 bromines together are the oxidation number. The individual charge is the oxidation number. Okay, so I have a challenge here. I go to iron, and if you look at your reference tables, you'll see iron could be +2 or +3. Which one? Maybe it's already obvious to you which one, but I'm not really sure what's going on here. It's either +2 or +3. Okay, let's look at the bromine then. -1, +1, or +5. It's definitely going to be the -1 because the iron is positive, so the bromide has to be negative. Otherwise, this won't end up being a neutral compound. I expect my metal to be positive. I expect my non-metal to be negative. So that really pushes me towards the -1 charge on the bromide. Okay. -1. I put it here. Obviously, I'm going to need the +2 charge on the iron. Now the oxidation numbers are in blue. In black, I'm just doing the math. Okay, so if someone asked what's the oxidation number on the bromine, the answer would be -1. What's the oxidation number on the iron here? +2. I'm going to focus on just the iron. Put a +2 here. Okay. Using exactly the same logic, work out what the charge on this aluminum would be. Pretty obvious, right? Okay. The aluminum in this compound will be +3. And how about this iron? Will he be +2 or +3? Trick question. He's alone. He's 0. Okay. This is why we need oxidation numbers. If we didn't have the oxidation numbers, we wouldn't be able to figure out who's trading electrons behind the scenes. Now, not every reaction has electrons being traded behind the scenes, but many of them do, especially single replacement. Okay. But let's stop and make sure we know how to do oxidation numbers in a polyatomic ion. If I look at the sulfate ion, SO4 with a -2 charge. instead of everything adding up to 0, this is not a neutral compound, all the charges are going to add up to -2. So whatever the oxidation number of the sulfur is, plus 4 oxygens. Okay. Now if I look at sulfur, there's a bunch of different charges he could have, but the oxygen is almost always -2 when he's bonded to other things. So I'm more certain of the oxygen. Now I've seen open response questions like this where they say, find the oxidation number of the sulfur in this larger thing, whether it's a compound or a polyatomic ion. So if they're asking about the sulfur, leave him for last. Each oxygen is -2. Is it obvious what goes there? If not, or if you're tired, you just want to make sure, put an X there. Algebra is your friend. This is saying that X, the charge on the sulfur, minus 8 equals -2. And of course, the charge on the sulfur has to be a +6. His oxidation number is +6. Okay. I've seen this for sulfur. I've definitely seen it for chlorines in some of these larger compounds, like ClO4 minus, things like that. Okay, now let's talk about what kinds of reactions are and are not redox. This is a single replacement reaction, of course, and single replacement reactions are always redox. Always redox. And the reason is hiding in this word single. The aluminum here is single. That means he's an element, a pure element with 0 charge. And then he's not. So his charge has to change. And the other element that was in a compound and is now single, his charge has to change. This doesn't just happen by stealing dancing partners. There is an exchange of electrons behind the scenes. Combustion. Combustion is always redox. You've got some kind of hydrocarbon. You've got pure oxygen, carbon dioxide, and water. And it's really the oxygen that gives it away. Here's another pure element. What's his oxidation number? I'm hoping you said 0. So anytime you see a pure element with 0 charge in your reaction, and then later he's bonded to stuff, that is how you know it's a redox. That's going to be the giveaway. If you're looking for a redox reaction, look for something with a pure element. Okay. Double replacement is never redox. That's because they're already ionic compounds. The positive and negative charges are already in there. The metals have positive charges, the nonmetals have negative charges, and then they just trade places. So real quick, silver nitrate, NO3, and sodium chloride. Sodium nitrate, silver chloride. Do you see any pure elements alone that would be 0? Nope, I don't. If I went through and figured out all their charges, this would be like +1, -1, +1, -1, +1, -1, +1, -1. So even though there's an exchange of atoms and ions, there are not any electrons being traded behind the scenes. Charges do not change, and that's why it's not a redox. Okay, now let's get into what to know. We're going to use this single replacement reaction to see if we can generate our redox chart, the chart that we really want to memorize. Everything about oxidation that we want to memorize, everything about reduction that we want to memorize. Okay, look at what we've got going on. The aluminum goes from 0 up to a +3 charge. He is definitely undergoing one of these changes. Okay. The iron is going from a +2 charge down to 0. He is definitely undergoing the other change. How do you remember what's what? Well, the first thing to remember about oxidation reduction is Leo the lion says grr. Leo says grr. Loss of electrons is oxidation, gain of electrons is reduction. Now, what does that do to your charge? You've got to remember that electrons themselves are negative. If you remember that, everything is going to make sense. So, tell me what happens with your charge. If you lose these negative electrons, you're losing garbage, you're losing negative things, don't you feel better? The charge should go up, usually from 0 up to a positive charge. But it could be any increase in charge. It could be a +2 up to a +4. If you gain electrons, you gain these negative guys, these garbage guys. You gain more negative stuff. You feel worse. Your charge goes down. This actually does make sense with the word reduction. Okay? This is almost more important than Leo says Gur. Remembering that electrons are negative, and if you lose those electrons, your charge goes up. If you gain those electrons, your charge goes down. We talked about this with the periodic table. Metals tend to do this. Non-metals tend to do this. In this situation, it's a battle between two metals. So one of them will be oxidized, one will be reduced. Okay, can you tell who is oxidized and who is reduced then? Take a moment and decide. Okay. Hopefully you've decided the aluminum is oxidized because its charge went up. So we're going to write the half reaction for the aluminum in this overall reaction. Half reactions are very, very, very simple. Pull out just the guy who is oxidized, if they're asking for an oxidation half reaction, and show the electrons being lost. If they want a reduction half reaction, pull out just the guy who's reduced, and show the electrons being gained. So let's do that for the aluminum. Pull out just the aluminum. Here he is with 0 charge. Then he has a +3 charge. Leave off the bromines. Leave off anything else. The only one being oxidized is the aluminum, so zoom in on him. Now, how would I show electrons being lost? I could put them on this side or this side. It's just like heat being lost is exothermic. We want the electrons on the right side. If it's oxidation, if they're being lost, we put them on the right, they're coming out. There's another way I can tell that the electrons go here, though. I always put the electrons on the side with the higher charge, because the charge, the total charge, has to balance. So if +3, this is the higher charge side, and I put 3 electrons here, they're negative, they're going to bring this charge down in balance. Okay? This guy now is 0 charge, and this all together, a +3 and 3 negatives, is also 0. So this is balanced for charge. They don't have to both be 0. They have to be the same, though. And if you have that rule of thumb, this is worth writing down, always add the electrons to the side with the higher charge. Okay. Keeping that in mind, let's show the reduction half reaction for the iron. First he's like that, then he's like that. Add the electrons to the side with the higher charge. Right here. It looks like I need 2 little negative electrons to get 0 charge balanced with 0 charge. Now these aren't the same, and that's okay because my reaction wasn't balanced originally. It might be obvious to you that the oxidation will have to happen twice and the reduction will have to happen 3 times. They'll work in whatever ratio makes sense. Cool. So we've got Leo says Gur, we've got the charge going up, charge going down. We have examples. We know how to write half reactions. Always put the electrons on the right if they're being lost, on the left if they're being gained. Now, why does this happen? In the past, we've looked at table J. Aluminum beats up iron and takes its bromides, right? Here's aluminum, and here's iron. Is aluminum strong enough to beat up iron? Yes. That's not really what it's about. If you have a voltaic cell, a spontaneous reaction, whatever metal is higher on table J, I picture oxygen bubbles floating upwards, it's going to be oxidized. Whatever metal is lower on table J, is going to be reduced. I want you to write this on your table J, and then when we get the Regents exam and you get clean tables, I want you to write it on those tables before you start your test. Whatever's oxidized will be the higher metal, whatever's reduced will be the lower metal for a spontaneous reaction for a voltaic cell. Now I know exactly what's happening. I know the aluminum is oxidized. I can take any of the facts that I already know. Say, oh, the aluminum is oxidized. He loses electrons and his charge goes up. The iron is reduced, he gains electrons and his charge goes down. All that stuff I already knew. However, I can also say which one is the anode and which one is the cathode now. So in a voltaic cell, if they give me the two metals, and I have my table J, as I always do, I'm going to know everything about that voltaic cell, including what is the anode, An-ox, and what is the cathode. Ooh, I should have done this in red. Red cat. And electrons always go from where they're lost to where they're gained. Grr. So add this. This is important. Add this to table J. A downward arrow with the electron symbol. They will always flow from whatever metal is higher on table J, the anode, to whatever metal is lower on table J, the cathode. So here's what we just added. We just added two facts. We added the anode is where oxidation happens, An-ox, and the cathode is where reduction happens because we picture a red cat, a little devil red cat. And then, if it's a voltaic cell, finally, whatever metal is higher on the activity series, on table J, whatever metal is higher, all of this will be true for it. It will be oxidized, it will be the anode. And whatever metal is lower on table J, all of this will be true. Okay. One thing they'll have you do is label the electron flow or describe the electron flow. So, aluminum and iron. If we had a voltaic cell, first of all, you would recognize that it's a voltaic cell because it would be in two separate containers connected by a salt bridge. One of the half reactions would happen in half cell 1, that's what they're going to call it. They're going to call it half cell 1 on the left, and the other half reaction will happen in half cell 2 on the right. And you'll have your electrodes. You'll have maybe a voltmeter, maybe something using the electricity. They might show a switch. Okay, obviously the switch will need to be closed. They'll say that somewhere in the problem that the switch is closed. And they'll ask for you to label the direction of electron flow. Now let's say that this is the aluminum and this is the iron. Do we now know everything? Absolutely. Okay. The electrons flow down the table. They're going to flow from aluminum to iron. So if I were going to describe the electron flow, I might draw it like this. They go from the aluminum up the wire, the switch has to close, through the voltmeter, down to the iron. They go from anode up through the wire to cathode. That is all the electrons do. They do not go back over the salt bridge. Salts go back over the salt bridge, specifically negative ions like nitrates and sulfates. You need the salty things to help close the circuit, but it's not electrons. Electrons go from anode to cathode and they finish their job because they do oxidation here, they do reduction here, and then they're done. Negative ions flow back over it to allow the circuit to continue. So how would you describe this if they said, what is the direction of electron flow? You could say from right to left. You could say the electrons flow from aluminum to iron. Or you could say the electrons flow from half cell 2 to half cell 1. And that question shows up on the Regents a lot. Also, the half reaction. Writing a half reaction shows up on the Regents a lot. If you're writing a half reaction, they will give you the full reaction. They'll give you like the Al plus FeBr2, like we saw before. And you'll pull out just the oxidation or just the reduction. Or they might say, what's the half reaction that happens in half cell 1? Guess what? It's the one that the iron does. What's the half reaction that happens in half cell 2? It's the one with the aluminum. Okay. So that is how to do oxidation numbers in compounds and polyatomic ions. What kinds of reactions are redox? Mostly single replacement and combustion. Know the chart, the redox chart. Okay. Look at everything that is on this chart now. Were we able to generate this chart? What it looks like in reactions, pull out the half reactions, and in voltaic cells. This is especially going to use table J. Now, voltaic versus electrolytic cells. We have this chart. Okay. I've seen questions where they ask for similarities and differences. So, similarities, they're both doing redox reactions, right? They both involve the movement of electrons. Differences, though, 2 half cells, 1 cell. This guy needs a battery. Now, this is not trivial. The fact that he needs a battery because without that battery, you wouldn't be turning that electrical energy into chemistry. And without the battery, see that word non-spontaneous? Without the battery, nothing would happen. So, electrolytic, it's not a coincidence that the electrolytic cell starts with electricity and forces a chemical reaction to happen. Often, this will be like a spoon and maybe a piece of silver or gold, plating the silverware with a precious metal on the outside, forcing the metal to bind to the outside layer. This guy is a battery, but it won't look like a battery. Nothing is happening in here. If you build this, it's amazing. You hook everything up, and voltage just happens. There's something about volt in voltaic cell. I picture a big volt, a big zap, that helps me remember that the reaction is spontaneous. The chemistry happens all on its own, it makes electricity. It almost seems like a miracle. Okay, other things are the same. The oxidation happens at the anode. Reduction happens at the cathode. All the other facts on this side of the chart, you can still trust in either of the cells. Okay, this has been topic 9. Thank you very much, and start working on your topic 9 questions.